Thank you very much, and thank you as well for the very kind invitation and also the introduction. I do hope there won't be any technical issues. On my side, the screen is flickering a bit, but I think you probably see my slides. Yeah, and I want to present today about a recent preprint that we put on the archive about light-controlled nanomagnetic computation. And that was a very nice collaboration I did here at CIC nanoGUNE in the Basque country in Spain. GUNE is a place, it's a place for nanomaterials. And the work was done in collaboration with Paolo Vavasori, Matteo Pancari, and also Jonathan Lilliard and Peter Gibbons at Ghent University, and also Matteo Mimit. Sorry. Okay, so what's the general idea about technology? And so as a motivation, we know now that we consume a lot of energy for a lot of different things, but also that energy consumption for computation will increase massively in the coming years. This is a prediction from kind of 3 years ago, might look different now, but the prediction was that in 2030, 20% of the electricity demand of the world will be consumed by communication technology and computation. And the reason is that we use way more data, we use way more computation, and we also have way more demanding problems to solve, like data classification, optimization of processes, learning and predictions, and so on. And the technology tries to keep up. There's the push to kind of more to try to make the nodes smaller in semiconductor industry, but we're approaching the physical limits. And there are also alternative approaches to computation, which is kind of, if you look on the international roadmaps for devices and systems, there's kind of more and beyond Boolean, where scientists and also technology tries to explore novel architectures, novel materials to kind of make more efficient computing possible. Quantum computing is one way to go, but today I want to talk about magnetism. So if you think about in the past years, I mean, this is something that I find very fascinating, different ideas how to approach computation of complex problems using specialized hardware. And there are different ways that you find in literature how it can be done. And the energy efficiency often comes from the fact that you use a system or a process that is very well suited to your problem at hand. So you try to find a system that kind of conforms with the natural data structure to solve hard problems, like optimization, for example. Also, there's a push to kind of go away from this Boolean logic, from yes, no, to some probabilistic results. Maybe if you want to optimize, you don't necessarily need to have the best answer, but you want to have a very good answer. So here are kind of different, very schematically different ways how you can do that. You can use quasi-particles, for example, domain walls or skyrmions, and count them because they can annihilate and can be created. You can have spin-wave dynamics, and this is actually 2 talks in this sessions are about magnons and magnonics because they can be very fast. You can parallelize things, you have your long distance transfer, and you can use kind of analog input variables of waves. There is also this very interesting works about synchronized nano oscillators to do classification or live classification of vowels, for example. And today I want to talk about using thermal relaxation as a way to compute things using nanomagnets. So the idea is the following, to kind of as a way to compute. You take an interacting system, and I will talk about that interacting system in a bit, and the solution of your problem is a low energy state of this interacting system, which can be reached by a suitable annealing procedure. So there's an operation cycle, you initialize your system, and the initialization kind of corresponds to your input of your computation, you let it relax, and then you measure the output, the final state, or kind of a sub part of the system, and that is your answer. We can do that in a nanomagnetic system where we store binary information in Ising macrospins. These macrospins are coupled using stray fields, and then you can create different gates. For example, this majority gate, you have, due to the coupling, a voting system on the central island. To be a bit more precise, or kind of before I will talk about these ingredients in a bit, but there are certain advantages using magnets because you have this coupling, straight feed coupling, you don't need wires. In principle, if you have very small nanomagnets, they're also low power switching, close to the Landauer limit. The nanomagnets store the information, so they're non-volatile, and also compared to, or in contrast to charge-based computation, magnets are radiation hard, so therefore there are fewer bit errors by some cosmic radiation. As a bit of a historical overview, there have been a lot of discussions using nanomagnets for Boolean logic. So again, kind of taking yes, no, and then answering is A and B equals, is A and B true? But in recent years, there has been a lot more discussion on how to use these systems because they're kind of icing systems and also inspired by the field of artificial twin systems to use this as solvers for optimization problems. With respect to the ingredients, I'm now talking about kind of purely two-dimensional arrangements of nanomagnets. These can be fabricated using nanolithography methods like electron lithography. And what you can do is if you make a magnetic material, a magnetic particle small enough, you get a single domain particle. In this case, we often use materials like permalloy, which is a nickel iron alloy, which is very soft. And then the critical length scale is in the order of 500 nanometers. So this is kind of here a magnetic force microscopy image of ellipses in the plane. And when you make them very small, they go from a multi-domain state or this vortex state to a quasi-uniform magnetization, a macrospin. And because the shape determines kind of the direction of the macrospin, it can have two stable positions, and there is an energy difference between those two possible states. And typical moments of these macrospins is in the order of 10 to the 4th, so 10,000 to a million millibars. So it's very classical objects. Those macrospins couple in first order by the point dipole interaction, which has this formula, which describes the so-called head-to-tail rule. So depending on how you place, because of this spin space mixing term here, depending how you place your nanomagnet in the plane, you will have preferably a ferromagnetic alignment or an antiferromagnetic alignment. And that means, depending how you put your nanomagnets onto arrange them in space, you will get complicated magnetic states, or kind of different states that can either be antiferromagnetic or ferromagnetic in the lower energy state. Coming back to the computation aspect, just as an example, to this operation cycle, typically in these experiments, you initialize your configuration, your spin structure, which is set by your lithography, by applying a magnetic field, in this case, kind of to the bottom left diagonal, and all the moments will point in that direction. Then you let your system relax, and then after some time, you look again and see what the structure, the magnetic structure is like. So what I plotted here in this kind of plane is an energy landscape for this particular system, where each lattice point corresponds to a particular magnetic configuration, and the height of this point corresponds to its energy. And the transition from this initial state to one of the ground states, for example, shown here, is done by successive flips of individual moments. And in this case, you flip 6 moments, and you can have, because you can flip them independently, in principle, you can have 720 possible pathways to the ground state. And because you can flip each of these one by one. This is one of the pathways, and as you can see, sometimes there are spin flips that would lead to a slightly higher energy. And that is actually not very good if you want to have a very reliable computation operation. So in principle, what you're interested in is going to some lower energy state, as kind of smoothly as possible. And this is actually one of the reasons why former implementations of nanomagnetic logic often failed a little bit, because you can have a lot of competing pathways and you don't necessarily select one that is kind of very smooth going to the ground state. So a lot of Boolean gates with nanomagnetic logic required a lot of engineering, and they didn't necessarily work very well because they were reliant on these kind of thermally induced relaxation processes, which are stochastic. To understand a little bit more is kind of the energy of the system is one way. So you can have like, okay, the ground state is my answer, but the important question is how do you get to the low energy state or the ground state of the system? And for that, you have to consider the kinetics, and which are governed by the Arrhenius law, where you have here a rate, a fluctuation rate, which is dependent on the stem frequency times an exponent of this barrier energy over kBt. So if you have like just a single nanomagnet, you have this degenerate state, you have an energy barrier, which is related to the shape anisotropy or any other anisotropy present in the system, and then with a certain rate at a certain temperature, you have a certain fluctuation. So of course, if you have an interacting system, your system, when it can relax, if there's thermal energy to induce relaxation, it will go to a lower energy state. But these barrier energies, energy barriers depend not only on the spatial arrangement, on the initial configuration, but they also depend on the rotations, and which we kind of described here. So this kind of gives you some time scale associated with that. What I wanted to talk about today is the other ingredient in this that describes the kinetic, and that is the temperature. Because typically this cannot be controlled very well, and I explain why. So in a normal experiment, or kind of typical nanomagnetic logic experiment, you take your sample, which is patterned on a silicon substrate, and you put it on a heater or a hot plate, and then you heat it up and let it relax. But this heating, because you have to heat everything, is slow. A lot of the experiments using photoelectron emission microscopy at synchrotrons, for example, take hours to kind of follow up when the moments are flipping, and it's also homogeneous. And this is something different that we showed here in collaboration with Paolo Vavasori and Matteo Pancaldi, how to use optical heating using thermoplasmonic excitations to introduce fast and localized heating with sublattice specific control using light. And that is actually quite nice and gives really novel ways how to affect nanomagnetic computation. So let me walk you through how that works. Similar to making a normal nanomagnetic system, you can use electron lithography, but instead of just growing your magnetic material, like the permalloy here, you also grow a thin layer of gold to create a hybrid nanomagnetic, a hybrid metamaterial, which combines magnetic properties and plasmonic properties. So these gold particles have the exact size to create optical excitations of localized surface plasmon resonances at visible and infrared light wavelength. So if you look at the optical properties of such a joint particle and look at the extinction, which is basically you look what light is getting lost in transmission, and the reasons of what can get lost is kind of due to scattering, due to reflection, and due to absorption. And this absorption is particularly enhanced whenever you hit this localized surface plasmon resonance. And this absorption leads to internal currents, which then lead to heating. And this is kind of the wavelength, and you get kind of the plasmon peak here at 800 nanometers. And if you use a light polarization perpendicular, so that is a light along the short axis of this ellipse, you get one at 630 nanometers. And you can compare that also to this simulated absorption cross-section, which gives the absorbed part of the light. If you look at the magnetic properties, you can do magneto-optical Kerr effect measurements, where you measure how the polarization of a reflected light beam changes as a measure of the magnetization of the material. And if you do a hysteresis loop, you see this typical bistable behavior that you would expect of this kind of Ising-like nanomagnet. Now, if we combine the two properties, we measure mode, but also illuminate from back with a laser that has been tuned to this plasma resonance, in this case, kind of 785 nanometers, and we increase the pump power of this laser light. You see that the coercive field decreases with increasing pump power, which means that the magnetic reversal is more efficient. And we can compare this kind of decrease in coercivity by using micromagnetic simulations, where we relate the decrease in the coercive field with the decrease in saturation magnetization. And that gives us a temperature scale, which in this case is kind of a temperature increase of 300 Kelvin. We can also relate that given a second temperature scale, which is equivalent, by taking the optical properties and the illumination conditions. And again, we get a temperature increase of 300 Kelvin. Now, the nice thing about plasmonic heating is that you can use this polarization-dependent absorption cross-section, as shown here. And just by changing the light polarization, then you can heat your system a lot or very little. So in this case, we have a laser at 785 nanometers, and we probe the Moog response under kind of heating. In this case, as shown on the previous slide, we have a reduction of the coercive field of 50%. But if we rotate the polarization, but don't change anything else in the setup, we have a very little reduction, which is directly related to this kind of absorption cross-section, which happens in the gold part of the part. And with that, one can directly think of having a kind of sublattice-specific heating, where we have moments, nanomagnets in two orientations, and then we can heat optically one sublattice while the other one stays cold. It's not exactly true. So this is a control experiment, so to say. We do Moog experiments with the magnetic field along the black direction. And then we either heat this black sublattice, which is the red line. You see a coercive decrease of 25%. And if we heat just the other sublattice, we would expect the black one to remain cold. But in this case, we still have a reduction of 15% of the coercive field. And the reason is that we have some thermal diffusion of these very hot islands to the neighboring islands of different orientation. One can fortunately tune the selectivity by, for example, changing how many heaters are illuminated. That is kind of tuning the self-heating versus a collective heating. And also one can play with this by changing the pulse length of the laser, because the plasmonic heating itself happens on picosecond time scales, and you get kind of an equilibrium temperature inside the particle. And the thermal diffusion through the substrate happens on much longer time scales that are in the nanosecond machine. And taking this approach, I now want to show you how you can create a reconfigure nanomagnetic logic gate. So just as a very slight recap, you have this using plasmonic heating on this hybrid systems. You can have like local fast and selective heating, and you have all these optical degrees of freedom for additional control. Like you can change light intensity to increase the temperature increase. You can choose where to heat, you can choose which sublattice to heat, and you can also heat on fast timescales. And that enables novel studies. One of them is kind of using kind of like an artificial spin system, and look if it's in a non-equilibrium condition, one sublattice is fluctuating at different rates. Also, what I wanted to relate it to this talk, implement a Boolean gate where we have a very controlled way of relaxation. So if you want to design a Boolean gate, you need different components. You have two inputs, one output, and it's often very helpful to have a bias that sets the energy. If we have this kind of, the inputs need to be set independently, so that's the reason why I put them at a 90-degree angle. And if you then apply a field in different directions, you can set all the four possible input states. But if you look at the energy landscape, so you see that these are kind of in kind of field set state, and whenever you have to kind of flip the output island, it would result in a high energy T3 state. So if you were to operate this gate by just heating the output island, you actually wouldn't get anywhere because nothing would change. So what we did with a little bit of engineering was to change the shape anisotropy of the input, where this is the bias, and the output gate, in order to address each of the individual islands individually. And with that, we are able to kind of set each of these possible states. This looks like this. This would be kind of the gate initialization. We set the input moments by applying a rotating field, and then we set the bias and the output moment always in the same manner. And then this results in different states, different magnetic configurations of different energy. Just as a reminder, this is kind of a notation from artificial spin ice. The higher the number after the T, the higher is the energy. And we can create these states also in the lab. And here are some magnetic force microscopy images showing possible configurations. Now, the important thing, of course, is how to operate the gate. And that is by heating specifically the output and let the system relax into a lower energy state. There is one thing that is kind of, so we use the plasmonic heating. In this case, we have kind of, if we have a polarization along the horizontal axis, each of these 4 islands will have a different absorption cross-section, and therefore it results in a different heating. And in this case, the output island is heated most efficiently. Also, to ensure that only the output island switches, but the input islands remain stable, we chose to use permalloy for the input islands and then nickel for the output islands, because nickel has a lower transition temperature than permalloy. And as you can see here, the kind of over time, after applying a laser pulse, we have a reduction of this nickel magnetization, and this indeed will be then the moment that switches. Or if we remain in the same state, if the kind of switch state would be in higher energy. We use a laser beam that is kind of focused on one of the gates, but all of the islands are illuminated in the same manner. Okay, and what if we do that? Unfortunately, now without experimental data, if we do that, these were the initial states that we set with the field state, and then we apply a horizontal polarized light to heat up the output moment. And then we end up in either a lower energy state, or we remain in the same state. And the output is equivalent to an AND gate. So kind of taking the inputs and the outputs, and it results in an AND gate. And using NUMAX simulations from Peter Giebens and Jonathan Leliard, you get a very high success rate with one exception. Here, I'll give you the reason following. There we go. So the reason is that during this heating process, you can calculate the energy, how it changes, and also whether you have a clockwise or counterclockwise rotation of the moment to the final state. And you get this very shallow barrier, and therefore there is a finite probability to kind of switch back while the gate is still, or while the output bit is still hot. And that leads to this reduced, success rate. But it's not very bad, because it can also be, by just changing the dimensions of the islands, changing the energy landscape slightly, that can be solved quite easily. And one thing that is quite remarkable is the laser pulse that we used for heating is in the order of 100 picojoule for one operation. If we compare that to kind of the energy consumption in kind of charge-based CMOS gate, that is in the order of attojoules, so several orders of magnitude better. But in this kind of nanomagnetic gate, we also have the results stored immediately, and therefore we can also compare this 100 picojoule with the 1 nanojoule per bit that is typically in the order of what one needs to kind of store data on a hard drive. One thing that is very nice as well is that we can control that it's not only an AND gate, we can also operate this as an OR gate by changing either the illumination conditions. So instead of just using horizontally polarized light, we can use both vertically polarized light and then another illumination with horizontally polarized light by kind of exciting first the bias island and then the output island, and we get an OR gate as a result. There's another way how you can set this by using a slightly different field for initialization, kind of pointing it downwards, and then it will also operate as an OR gate by just using one light pulse to excite the system. So we have a very versatile way, and this is actually something that is different from a lot of other nanomagnetic logic where the reconfigurability is actually done at the fabrication. In this case, we can really choose, because we can control how we heat our system, we can choose how the system relaxes. And with that, I'm already at my conclusion. I hope you got some insight how we can use thermoplasmonic heating. It's a very interesting technique, also in combination with magnetism, because you can heat in a very localized manner. You can create interesting temperature distributions to select these relaxation pathways in artificial spin systems. One advantage of using this plasmonic heating is also that it simplifies a lot the design of a nanomagnetic logic gate, because you don't have to, because you know very well which of the moment will switch. And in the future, because you can use light and you can shape light, you could also envision to use kind of like a distributed computing approach, both in this kind of gates, but also in some fluctuating systems. And I think that's quite interesting. And with that, I thank you for your attention.